Nowadays, questions such as what is the origin of this product? Under which criteria has it been manufactured? What impacts does it have? How will it be discarded? Are increasingly common in society, and it shows a growing interest in knowing what is behind each product. To answer these questions, it is necessary to use the life cycle concept to determine the complete route of each product, i.e., all the stages of a product system. From the initial phase, for example, raw material acquisition or generation from natural resources, to its final disposal. In the life cycle context, two different approaches can be applied. The first approach, from cradle to grave, analyzes the stages of the product's life from resource extraction, cradle, to the final disposal, grave, assuming that the products have only one use and cycle. This approach is associated with the linear economy. The second approach, from cradle to cradle, allows to give continuity to the life cycle of a product, connecting the final phase of a product with the production, distribution, or consumption phase. This approach is closely aligned with the circular economy, which has been presented previously. This section focuses on life cycle analysis, which assesses the potential environmental and social impacts of a product system throughout its life cycle. In particular, we explore the life cycle analysis of the following product, a cotton-made t-shirt. This product is one of the best-selling items of clothing in Europe. In order to carry out the life cycle assessment, we have to use the SIMA Pro tool with data provided by EcoInvent version 3.2 as a source of quantitative data in the environmental dimension, and with data provided by SHDB, a source of quantitative data in the social dimension. This section presents three scenarios that illustrate three different t-shirt life cycles, which are an approximation to the current situation of the textile sector. Scenario 1 assumes that the t-shirt is produced in different countries and it is thrown away to a landfill. It is not considered reuse. Therefore, this scenario is associated with the linear economy. Scenario 2 adds a reuse phase in a low-income country. In this case, we consider the reuse phase, and this phase is more connected with the circular economy, although the life cycle defined in the Scenario 2 is not totally circular. Scenario 3 replicates Scenario 1, but in this case, all the phases are located in a high-income country, which is USA. This scenario is also aligned with the linear economy. Focusing on the first scenario, the characterization is as follows. The cotton for the t-shirt stems from the USA, 15.6%, China, 29.8%, and the rest of the world, mainly India and Pakistan, 54.6%. During the period of its use, it is estimated that on average, a t-shirt is washed and dried for 50 cycles. At the end of life phase, t-shirts are thrown away to a landfill in Germany, treatment of municipal solid waste, and no recycling is considered. The second scenario differs from the first scenario in the reuse phase, because in this scenario, the cotton-made t-shirt is reused as a second-hand item of clothing. Concretely, in this scenario, the use phase is divided into two stages. First, there is a phase of use in a developed country, Germany, where the t-shirt is washed and dried for 40 cycles during the period of use. After that, there is a reuse phase in a developing country, in this case Ivory Coast, where it is hand-washed for 25 cycles, thus extending the phase of use of the product. At the end of life phase, the t-shirt is treated as municipal solid waste, incinerated. The third scenario, a local market, has been defined. All companies and uses from the life cycle phases of the cotton-made t-shirt were in the USA. To know the impacts caused along the product's life cycle, we propose the use of science-based tools. In this respect, to assess the environmental and social impacts, the European Product/Organization Environmental Footprint and the Social Life Cycle Assessment of Products provided by UNEP SETAC are the most accepted technical tools in the market. We have applied both tools in the case of the t-shirt. The results presented in the tables have been calculated based on Scenario 2, since it shows the most complete reference, including a phase with a circular economy, the reuse phase, and a low-income country for the end of life of the product. The numbers mean the cumulative impact contribution of each life cycle phase to the overall impact by impact category. In this table, the impact categories have been ordered from the highest to the lowest level of significance of their impact. The results show that 50% of cumulative impact contribution to any impact category is reached in the two first phases of the product's life cycle. Combining these results with the aspects managed and reported by the companies analyzed in the section Environmental and Social Impacts of the Textile Sector, it is observed a clear gap of public, environmental, and social information in those phases where the impacts are more substantial. This implies that companies, when managing environmental and social issues, are ignoring those environmental issues actually relevant from a technical view, from a life cycle perspective, according to their activity nature and geographical location. In this slide, we present the assessment of the social and environmental impacts in the three scenarios. We can observe the most relevant impact categories. For instance, in the environmental dimension, we observe that the most important ones for the textile sector are 1. Water resource depletion, 2. Human toxicity cancer effects, 3. Freshwater ecotoxicity, and 4. Human toxicity non-cancer effects. We also can explore the difference between scenarios. We can observe that the difference in terms of the impacts by product in the scenario 1 and 2 are not substantial, since the majority of the impacts are originated in the first phases of the life cycle, and these phases are common for both scenarios. The differences in water resource depletion between scenarios 1-2 versus scenario 3 are due to the different agricultural techniques employed in cotton farming. In the case of ionizing radiation, a possible explanation regarding differences between scenarios 1-2 versus scenario 3 could be the presence of different electrical mixes and systems of generation of the electrical energy. Electricity in the USA has a greater component of nuclear energy, while electric power in China, and especially in the agricultural areas, comes mainly from hydraulic energy. With respect to the social dimension, we observe that the fall t-shirt life cycle developed in the United States shows better results in all the social categories analyzed. Nonetheless, impact categories like collective bargaining or toxics or hazards show a high impact that need to be managed. Note that the definition of the scenarios and the results come from the two deliverables that Sowers Research Group developed in the context of the European Horizon 2020 project, SMART project. Therefore, for more information, see Deliverable 5.2, List of best practices and KPIs of the textile products life cycle, and Deliverable 5.6, Testing Sustainability Assessment Tool in the selected case studies from textile and mobile phone sectors. As final remarks, we highlight the following. In a business context, there is a risk of bias in the environmental and social efforts to address those issues that have received more media interest at the expense of other relevant environmental and social impacts, especially considering all the phases of the product's life cycle. We need to apply science-based tools like the European Product/Organization Environmental Footprint and the Social Life Cycle Assessment of products provided by the UNEP SETAC to know the real environmental and the social impacts. Consequently, this is important to make informed decisions in the management of environmental and social risks. Circular economy practices are not sustainable by definition. It is important to measure the impacts of the different options/scenarios to choose the most sustainable one and manage the most relevant impacts, hotspots, to contribute towards the sustainable development.